Tesla is very wise. Elon Musk once explained why Tesla has not fully unveiled Optimus V3 yet, stating, "By the middle of this year, it'll be ready to show up." We're also a little hesitant to show V3 off because we find our competitors do a frame-by-frame analysis whenever we release something. They copy everything they possibly can. I think there is some value in not showing new technology till it's close to production. That statement clearly describes Tesla's position in the humanoid robotics industry today. The company is no longer just competing with rivals. It is increasingly becoming the engineering benchmark that others study and attempt to replicate. A clear example of this dynamic is Xiaomi's Cyber 1 V2, which was widely compared to Tesla's Optimus Gen 2, even though Tesla had already unveiled that version back in December 2023. In practice, by the time competitors analyze and copy one generation of Tesla hardware, Tesla has already moved on to developing the next one. That next stage is believed to be Optimus Gen 3. To support this next phase of expansion, Tesla is rapidly accelerating construction at the end campus area of Gigafactory Texas. Recent drone footage shows a massive diamond-shaped foundation beginning to take form, while GeoPier Foundation Company continues reinforcing deep support columns and expanding large-scale grading across the site. The scale of construction makes it clear that Tesla is not building a small robotics lab or a limited pilot production line. Instead, it is preparing infrastructure for humanoid robot manufacturing at true industrial scale. This level of investment aligns with Elon Musk's long-term belief that Optimus could eventually surpass Tesla's vehicle business in value and importance. Musk has stated that Optimus will be the biggest product ever of any kind, and also suggested that it could ultimately become more valuable than both Tesla's car business and its full self-driving technology. These statements make Tesla's strategy very explicit. Optimus is not a side project, but a future global robotic workforce platform designed to produce millions of humanoid robots annually. It is within this context that Tesla's newly revealed knee joint patent becomes especially significant. The knee is one of the most critical components in a humanoid robot because it carries the majority of mechanical load during walking, squatting, climbing stairs, lifting objects, and maintaining balance. Tesla's patent filings, including this one, describe a fundamentally different approach to this problem compared to traditional humanoid designs. Instead of relying on large gearboxes, multiple rotary motors, or clusters of actuators around the knee, Tesla developed a biologically inspired system based directly on human anatomy. The design uses a single compact linear actuator combined with a 4-bar linkage mechanism that replicates the biomechanics of the human leg. Tesla engineers studied how the femur, tibia, patella, quadriceps tendon, and patellar ligament work together to transfer force efficiently in the human body, and then translated those principles into mechanical structure. The result is a system capable of achieving around 150 degrees of flexion and extension, closely matching the natural human knee range of approximately 140 to 160 degrees. This allows Optimus to crouch, squat, walk, and climb stairs with movement patterns that appear significantly more natural than conventional humanoid robots. However, the most important innovation is not simply the range of motion, but the way that motion is produced. Inside the thigh, a compact linear actuator acts similarly to an artificial quadriceps muscle. Instead of rotating through large angles like traditional motors, the actuator only moves through roughly 60 degrees of travel. The 4-bar linkage then mechanically amplifies this smaller motion into approximately 150 degrees of lower leg rotation. In effect, Tesla has created a leverage system that mirrors how tendons and the kneecap amplify muscular force in the human body, allowing a relatively small actuator to generate a much larger and more efficient output movement. This approach fundamentally changes the economics of humanoid robotics. Traditional designs often require multiple rotary motors around the knee to generate sufficient torque and flexibility, sometimes using 2, 3, or even 4 actuators working together. While this increases power, it also introduces significant drawbacks, including higher weight, larger batteries, greater heat generation, more complex wiring, and increased manufacturing cost. Tesla's design avoids this by reducing mechanical complexity while maintaining or even improving performance. Because the actuator is smaller and more efficient, overall power consumption is reduced, lower energy demand allows for smaller batteries, and smaller batteries reduce total robot weight. Reduced weight then lowers torque requirements across all other joints in the robot, which in turn reduces energy consumption and heat generation throughout the entire system. This creates a cascading efficiency effect that improves performance while simultaneously lowering cost and complexity. Cost is the central constraint in humanoid robotics. Elon Musk has repeatedly stated that Optimus must eventually reach a production cost in the range of approximately $20,000 to $30,000 United States dollars to achieve mass adoption. However, most existing humanoid robots today remain in the range of $100,000 to $300,000 United States dollars and are produced more like research prototypes than scalable consumer products. Tesla's strategy is based on the belief that humanoid robots will only become mainstream if they are manufactured with automotive-level efficiency and scale. This is why the knee patent matters far beyond its mechanical design. Even small reductions in actuator count or weight become extremely significant when multiplied across millions of robots. A simpler knee design reduces material costs, simplifies assembly, lowers electronics requirements, reduces cooling needs, and decreases total system mass. When applied across both legs of every robot and scaled to annual production volumes of millions of units, the economic impact becomes extremely large. This also explains Tesla's manufacturing strategy. During its Q4 2025 earnings call, Tesla outlined plans for an Optimus production line targeting 1 million units per year at Fremont, with even larger long-term expansion planned at Gigafactory Texas. The company has already begun restructuring parts of its Fremont operations to accommodate Optimus manufacturing, including shifting away from legacy vehicle production areas. Competitors are already responding to Tesla's direction. When XPeng introduced its next-generation iron humanoid robot in late 2025, analysts quickly identified similarities between its knee architecture and Tesla's Optimus system. The design appeared to incorporate a modified reversed hook and linkage and similar hip configurations. By that time, Tesla had already publicly demonstrated comparable concepts years earlier during AI Day and had documented them extensively in international patent filings. This highlights Tesla's true advantage. The company is not only advancing faster than competitors, it is establishing a full mechanical and manufacturing framework that others are still attempting to replicate. Ultimately, solving humanoid robotics is not just about artificial intelligence. It is about solving the physical, economic, and manufacturing constraints of human-like movement at scale. For decades, the knee joint has been one of the key engineering bottlenecks preventing humanoid robots from becoming commercially viable. Tesla's approach, using biological inspiration, linkage geometry, and actuator simplification, appears to remove much of that barrier. This is no longer a conceptual vision. The system has been patented, demonstrated in engineering direction, and is actively being integrated into future Optimus generations. That is why this innovation matters so much. It is not just a knee design. It may represent one of the foundational building blocks enabling Tesla's long-term goal of mass-producing millions of humanoid robots and reshaping the global robotics industry. Why would Tesla dare to discontinue its legendary car models just to make way for robots? The devastating difference between Tesla and the rest of the robotics world doesn't lie in who creates a smarter prototype in the lab. Elon Musk's ultimate weapon is his industrialization and mass production capabilities, something no other robotics company on Earth has dared to dream of. Let's face the reality. While most of its formidable competitors are still manually producing a few dozen to a few hundred robots each year as expensive tech gadgets, Tesla has quietly built a production infrastructure capable of pumping millions of humanoid robots onto the market. Is it insane for Tesla to be willing to abandon its core heritage just to make way for soulless metal monsters? The answer was confirmed by a historic action at the Fremont, California plant in the first quarter of 2026. Tesla has made a ruthless decision to halt global production of its two iconic luxury electric vehicles. The Model S and Model X, the final signature edition vehicles, rolled off the Fremont production line on May 9, 2026, officially closing an era of luxury cars to make way for robots. The entire factory area was completely restructured into a first-generation Optimus production line with the Optimus 5.3 as its core, aiming for an initial capacity of up to 1 million robots per year. Elon Musk stated frankly in the Q4 2025 earnings call that transportation is no longer Tesla's sole core product, and that Optimus is the focus of the corporation's next chapter. But Fremont was just the starting point for a true manufacturing monster taking shape at the Texas Gigafactory. Construction plans in Austin are revealing a massive construction site of unimaginable scale. To accommodate the massive production of the Optimus 5.4, Tesla has leveled and expanded the N campus, located right next to the old Texas Gigafactory. Field reports and satellite imagery from early 2026 revealed massive diamond-shaped foundation blocks emerging, along with thousands of heavy-duty geopier foundation columns being driven into the ground. Tesla has filed for permits to build more than 5,200,000 square feet of new factory space at its North Campus. bringing the total floor area of the Giga Texas Supercomplex to a record 15 million square feet by the end of 2026. This isn't a test robot factory, it's a specialized megafactory designed to realize Elon Musk's outlandish ambition, producing 10 million Optimus robots per year. This manufacturing power is backed by a massive financial resource that no startup or robotics corporation could ever dream of. In its financial report for early 2026, Tesla confirmed that its capital expenditure plan for the year would exceed $20 billion. A large portion of this money was invested directly in building 6 new production lines related to robotics, batteries, power, and especially a Cortex-1 and 2 supercomputer system in Texas, possessing the power equivalent to more than 230,000 NVIDIA H100 graphics processing units to train AI for the robots. Tesla even manufactured its own AI-5 processor chip, the specialized reasoning brain for Optimus, with the design completed in April 2026. Is there any competitor in the robotics industry that can rival a madman willing to spend between $5 and $10 billion on the infrastructure of a single robotics factory? However, the path from a smooth demonstrating prototype at the ETH Zurich exhibition to a million robots operating reliably in harsh industrial environments is a deep chasm. Elon Musk frankly admitted in Q1 2026 that no Optimus robots were actually performing useful work on a large scale inside Tesla factories, and the goal of deploying 10,000 robots internally by 2025 had been missed. This delay is an inevitable reality of the manufacturing industry. A robot performing a few skillful maneuvers in Shanghai doesn't mean it can work continuously for thousands of hours without battery drain, motor overheating, or visual FSD system failures. Therefore, the commercialization timeline has been repeatedly adjusted. The Fremont test version has been pushed back to the end of summer 2026. The first business-to-business customers are expected to access the robot by the end of 2026. And the mass-market consumer version with a target price of $20,000 to $30,000 has been delayed until the end of 2027. But can these short-term setbacks stop Tesla? The answer is no. Tesla's delays are actually part of the process of perfecting the mechanical structure, such as increasing the thickness of the forearm to accommodate the 25 advanced actuators and optimizing the automated assembly line using robots. When Tesla solves the problem of automated mass production, making machines make machines, they will create a massive supply shock. With millions of units shipped annually from Fremont and Texas, Tesla will not only reshape the robotics industry, but will directly change the definition of the global workforce and supply chain. If you'd like to learn more about the actual operation of next-generation robotic arms and the progress of infrastructure construction in Austin, you can watch the detailed video below for the most visual understanding of the enormous scale and lightning-fast pace of construction at the Austin mega construction site. Check out this live drone footage, Giga Texas N campus expansion. This video details the progress of foundation construction and site leveling for the N campus, where Tesla's multi-million-dollar Optimus manufacturing plant will be located by mid-2026.